Please note that I'm skipping the first page. It's not because it's not important, it's because I assume you can read. Please read that page. Okay. In this particular section that you see right here with my handwriting, it is really important that you not just listen and look. It is really important that you get out your graphing calculator so that you understand the relationship between a Taylor polynomial that approximates a function and the actual function. This particular example of sine of x seems pretty nonsensical, right? This is sine x right here, and this is the Taylor approximation. It's not important that you understand what a Taylor approximation is yet, or a Taylor polynomial is yet. What you need to understand right now in this moment is that you will be able to approximate values for functions that you were not able to integrate before now using these Taylor polynomials and Taylor series. So in this particular instance, it's not useful. It becomes useful later on. Okay, so make sure you actually graph y sub 1 equals sine of x and y sub 2 equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. If you look carefully at your two graphs, you're going to see that they look almost identical. And they are more identical the closer you get to their center, which is x equals 0. If you are to add more terms, the graphs actually become more alike for a longer period of time. And you need to make sure that you also graph this second one that I've created, or this second Taylor polynomial that is written down in purple handwriting where I've extended it out 2 more terms. And if you want, you could even add more terms just to mess with it a little bit. But it's really important that you graph that. I think I said that like 10 times. It's important that you graph it. On the lower part of this page, or I guess it's actually the middle of your paper page, you see something that looks extremely visually confusing. I think this is why people are confused about Taylor polynomials. I mean, this just straight up looks like gibberish, and so does this. They aren't as gibberishy as you think. It just really is visually confusing. Right now, all I want you to remember is that a Taylor polynomial can be centered at any value of x, but a Maclaurin polynomial is centered at 0. So you need to know the difference between those two terms. So a Maclaurin polynomial is actually a Taylor polynomial. It's just a specific kind of Taylor polynomial. Now we're going to write a Taylor polynomial of degree 3 for f centered at 2. And although the actual formula is visually confusing, you are going to see that the actual math is not too complicated. It's kind of busy work. Okay, if you look carefully here, I have used the values. Sorry about the bell. If you look carefully here, I have used the values in our function, and we don't even know what that function is. But I'd like you to notice that this first function here, this first term here, corresponds with the original function value. The second term here corresponds with the first derivative and x minus 2 to the 1 all over 1 factorial, which is just 1. So if we were to look back at the first one, you could see Or if you look carefully, you can see that that is times x minus 2 to the 0th, all over 0 factorial. For those of you who don't know, 0 factorial is just 1. So everything matches up. When you have the first derivative, you also have the first power. When you have the first derivative, not only do you have the first power, but you also have the first factorial. So second derivative, second power, second factorial. Okay, back up to the first line where I completely worked it out. You can see there that the math is pretty simple. I hardly did any math there. There's no need to simplify what you see there. On this next example, you're going to create a Taylor polynomial of degree n equals 4 for f of x. So we go ahead and find our function at 2, our first derivative, our second derivative, our third derivative, and our fourth derivative at x equals 2. It is really important to note that they are asking for a polynomial of degree 4. They are not asking for 4 terms, and they will ask for both to try to confuse you. Now, using that same formula, we can create a Taylor polynomial of degree n equals 4 for the function f of x. And we don't need to simplify. You can generate your Maclaurin polynomial for degree n equals 5 for f of x equals sine x using that same formula, but I put a special note in here. Sometimes they will ask for p sub 5. P stands for polynomial, or they might ask for m sub 5, where m stands for Maclaurin, or they might ask for t sub 5, where t stands for Taylor. Any one of those notations mean the same thing. And also, there's something else I wanted to talk about real quick. Just a reminder that a Maclaurin series is a Taylor series centered at 0. So they could ask you for a Taylor series centered at 0, and they would be asking for Maclaurin series. It's the same difference. Don't let the verbiage trip you up. Using your calculator, you can find the value of both the approximate value of both the Taylor polynomial at 1.4 and the function value at 1.4. Using that information, you can find the error in your approximation. It is important to note that your error will always be an absolute value. Now I want you to go ahead and try to find the Taylor polynomial approximation at 2.1 and the function value at 2.1 using your calculator.
I'm good. Are you recording?
When you did your calculations, you should have gotten a polynomial approximation of 0.89684, and your function value at 2.1 should have been 0.86321, and your error should have been 0.02763. If you look, the error in C is larger than B. Hey, guess why? Because you are farther from the center. The center is 0. The farther you are away from 0, the larger your error will be. What this means is if the polynomial is centered at x equals 3, the approximation p sub 5 at 2.7 would be the most accurate of the three. This is a repeat of previous information. There is nothing new here. Here you see a reference to the Lagrange form of the remainder and the Lagrange error bound. You won't be studying that until much later. When we look at this graph, we can see that the y-intercept is positive, which would be the function value at 0. The first derivative at 0 gives us a slope at 0, which is also positive. But the second derivative at 0 gives us 2c, which must be negative because the function is concave down. The way I found the value of f of 4 and f double prime of 4 was I set these pieces, this piece equal to each other, or those two pieces equal to each other, and these two pieces equal to each other, because they must be equal. And f of 4 is quite obviously 2. F double prime of 4, in order to solve for it, you need to, sorry, I'm still not good with this thing. You need to set these two pieces equal, and you see pretty quickly that if you set those two pieces equal right there, that x minus 4 squared is on both sides, so that cancels. So f double prime of 4 over 2 prime must equal negative 5. So f double prime of 4, when you solve, when you get f double prime of 4 on both sides and everything else on the other, you get negative 5 times 2 factorial, which is just 10. And the last one, the 8, you also do the same way. I just haven't written that out. So here we go. I set the two pieces equal. I cancel the x minus 4 cubed. And you get f double prime of 4 equal to 8 times 3 factorial, which lo and behold equals 48. Using the formula and the information given, you can create the third degree polynomial for f about x equals 3. This is just simply plugging things into the polynomial. Okay, when it asks if it's a maximum or a minimum at x equals 4, you can look by the second derivative test. You have the first derivative equal to 0 and the second derivative is negative. Therefore, it must be a maximum. There must be a local maximum at x equals 4. And you need to justify your answer using those words. You need to mention that you use the second derivative test or the first derivative test, but in this case it would be the second derivative test. So on A, you generate your third degree Taylor polynomial using the formula, and you don't even need to know what the function is here. Pretty simple. I mean, it looks crazy, but the actual math is just busy work. When you replace x with x squared plus 3, you actually end up with an expression that says x squared plus 3 minus 3. So your 3's go away, well, cancel, whatever. And you end up with a pretty Taylor polynomial, negative 4 plus 2x squared plus 7 halves x to the 4th. Lastly, here's your meme of the day. I only put one in this time. I felt like last time I kind of overdid it. But every single meme in both the last slideshow and this slideshow are actually designed to help you review.